So this is a quick tutorial explaining 6 simple steps for testing whether or not a population is in Hardy-Weinberg equilibrium. So for example, if we're posed with this question, that in gray wolves, black coat color is caused by a dominant allele B, and that in a population of 500 wolves, we find the following genotypes given in this table. So we have 75 homozygous dominant individuals, 275 heterozygous individuals, and 150 homozygous recessive individuals. And we want to know, is this population in Hardy-Weinberg equilibrium at this locus? So the first thing we want to do is calculate the allele frequencies. So remember that P plus Q equals 1, and P and Q represent the different alleles. In this case, it's uppercase B and lowercase b, which are the dominant and the recessive alleles for coat color. But also remember that P squared plus 2PQ plus Q squared equals 1, and P squared, 2PQ, and Q squared represent the 3 different genotypes. So if we're going to calculate the allele frequencies, we see that we have 500 wolves and each of those has 2 alleles. So if we're looking at the total number of alleles in the population, that's 1,000 alleles because each wolf has 2, either a big B or a little b. So if we're going to calculate the frequency of the dominant allele, that's represented by P, and we count up all the number of dominant alleles divided by the total number of alleles. And we get 75 times 2 plus 275 divided by 1,000. Now the reason 75 is multiplied by 2 is because there's 75 homozygous dominant individuals, and each of those individuals carry 2 dominant alleles, but then we have 275 heterozygous individuals which only carry 1 of the dominant alleles. And if we calculate that, we get a frequency of 0.425. Now we can do the same thing with the recessive allele. So Q equals the frequency of the recessive allele. And what we do is we count up the total number of recessive alleles divided by the total number of all alleles. And the same as before, we have 150 times 2 plus 275 over 1,000. Now 150 times 2, that's because there's 150 homozygous recessive individuals. And again, 275 heterozygous individuals. And that gives us a value of 0.575. But remember that P plus Q equals 1, so we could have calculated Q a little bit more simply by subtracting P from 1. And if we do that, we get 1 minus 0.425, which gives us a value of 0.575, which is the same as the frequency that we got by doing the other calculation. So the next step is to calculate the expected genotype frequencies. So if we're looking at our frequency of P, which is the frequency of the dominant allele, and we look at the frequency of the recessive allele, we can calculate out the expected frequencies of the different genotypes. For example, the expected frequency of the homozygous dominant is equal to P squared, which equals 0.425 squared, which comes out as 0.181. Similarly, we can do the calculation for the heterozygous individuals, which equals 2PQ, which is equal to 2 times 0.425 times 0.575, which calculates to 0.489. And finally, we can also do the frequency of the homozygous recessive, which is represented by Q squared, which equals 0.575 squared, which comes out to 0.331. So as a side note, we could have calculated Q squared a little bit differently by using the formula P squared plus 2PQ plus Q squared equals 1. And that's because Q squared is equal to 1 minus the frequency of the 2 other genotypes. And we know that the expected frequency of the homozygous dominant genotype was 0.181, and the frequency of the heterozygous individuals was 0.489. So by using our formula, we can calculate out that the frequency of the homozygous recessive is equal to 0.330. Now in the previous example it came out as 0.331, and that's just due to rounding error. But you can see there's 2 different ways to calculate that value. So step 3 is to calculate the number of individuals with the expected genotypes. And this is a simple calculation because we multiply the expected frequency of each genotype by the total number of individuals in the population. So the expected number of homozygous dominant individuals is 0.181 times 500, which equals 90.5. Similarly, the expected number of heterozygote individuals is 2pq times 500, which comes out as 244.5. And finally, the expected number of homozygous recessive individuals comes out as 165.5 individuals. So the next step is to calculate the chi-squared statistic. So the chi-squared formula is the sum of the observed minus the expected value squared divided by the expected values. For our data set, we're looking at the observed number of individuals and the expected number of individuals shown in the table. So if we're going to calculate chi-square, we take 75, the number of observed individuals, minus 90.5 squared, all over the expected number of individuals, and then we do that for each of the 3 different genotypes that we saw. And if we calculate that out, we get 200.655 plus 3.805 plus 1.452, which comes out to being 7.912. So that's our chi-square statistic. So step 5 is calculating the degrees of freedom. And for us, the degrees of freedom are equal to the number of genotypes minus the number of alleles, which is equal to 3 minus 2, or 1. So finally, step 6 is to find the chi-square value that you calculated on a table of critical values for the chi-square distribution. So we calculated the degrees of freedom as 1, and we calculated the chi-square to be 7.912. So then we refer to a table of the chi-square distribution, and we look for where our degrees of freedom are. In our case, it's 1. So then we follow that over until we find a value close to our chi-square statistic. And in this case, ours is actually a little bit higher than the highest value for 1 degree of freedom. And that's okay, because we can say that actually the probability is less than 0.005, because in reality, our chi-square statistic would be further to the right. So we have a p-value of 0.005. So what exactly does this mean? So this means that the probability that the observed genotype frequencies are what we expect is 0.005 or 0.5%, and that's pretty low. So if the population was in Hardy-Weinberg equilibrium, the observed genotype frequencies would be very similar to the expected frequencies. In this case, it's very unlikely. So we can say that this population is not in Hardy-Weinberg equilibrium, at this locus anyway, because that's the data we've been presented with. So if a population is not in Hardy-Weinberg equilibrium, this suggests we could dig deeper to find out why. Maybe there's migration that allows gene flow between 2 populations, or maybe there's inbreeding, or it may even be a technical issue with our genotyping. Perhaps there's null alleles or allelic dropout or other scoring errors. So the Hardy-Weinberg equilibrium is the first step in understanding whether or not our population is following the expected rules of Hardy-Weinberg.